ADP days.
You will go to their hotel tomorrow, right?
Yes, you can go tomorrow morning.
Yes, I will.
Good luck. Then don't, just don't talk.
Depends, like you're arriving in only now because of the weather.
Okay, so
Nobody else is.
3 seconds.
So you should. Sorry, you should.
Yeah.
Doing a bit of planning.
I see, okay.
Oh. So the last talk of today is Rasmus Jaksland, who's talking to us about the versatility of spacetime.
Yes. So I fear this will be perfectly orthogonal to anything anyone said anything about, and possibly what anyone is interested in. So I apologize beforehand, but at least it will offer another perspective on space-time functionalism. So we do the usual sort of thing here from the analog to the philosophy of mind. We say functionalism, and here I bolded this particular piece, is the view that, in this case, mental states do not depend on the internal constitution of the being that realizes them. So the mental states are characterized by the role they play. Okay, and functionalism in the philosophy of mind is often contrasted with identity theory. So exactly the view that it is the internal constitution of the being that we should identify mental states with. Okay, this will be important for this talk. So we can say identity theory is sort of a chauvinist theory. It wants to say that no matter how similar being is in terms of behavior or internal constitution, if they are not exactly similar to us, then they can, for instance, realize pain. So in this sense, we'll say identity theory is a very chauvinist theory. And I propose that an identity theory about space-time entails the same sort of thing, so that space-time is dependent on or equivalent to some particular internal constitution of our reality. So just rephrasing what we have up here from the Stanford Encyclopedia of Philosophy and Identity Theory, we will say that space-time identity theory entails that no realities with physics unlike ours can share space-time. Initially I had concept of space-time. Here I realize it will be a mess going into that particular regime. I want to sort of stay out of that discussion if possible at all. So I just say they share in space-time no matter how similar their behavior and internal organization may be to our own, that is our own reality. And I'll propose that what characterizes space-time functionalism is that it renounces this sort of chauvinism. Okay, so a defense of space-time functionalism as something that renounces this identity theorist chauvinism can take two paths, I think. First is the more usual path, and the path I think most have followed so far. It's to provide a convincing argument that there is some functional role of space-time and sort of offer this functional role, demonstrate that it does the sort of work we want space-time to do, so on and so forth. But if what we want is just an argument in favor of space-time functionalism, I propose a different route. So I propose route 2, namely to give an argument to the effect that space-time is topic neutral. So not dependent on this internal constitution, or not equivalent to a particular internal constitution. So particularly, as Vincent alluded to, there's some sort of, and I say it's what I hint at in the title as well, there's some versatility to space-time. And it's particularly independent of some concrete internal constitution. It's rather precisely a function. So I'll try to follow path 2 and then argue that space-time is multiple realizable in quantum gravity, that this is a consequence of topic neutrality and thus not merely an artifact of the type of quantum gravity theories we find interesting to pursue. So this will be the obvious objection that I'll consider later, namely that the immediate multiple realizability we find when it comes to space-time. It's just some artifact of the sort of theories we find interesting to pursue, and not actually an indication that space-time is genuinely topic neutral, and therefore something that we can employ in an argument for functionalism. Okay, so this is, I guess, the question I should address. So we can ask, why should we care about this? We are interested in space-time and not space-time functionalism as such. Our interest in space-time functionalism originates in an interest to know what space-time is. And following this path number 2 and arguing, just showing that space-time is multiple realizable or topic neutral, won't give us very much in terms of information about what space-time is. So we could say following path number 2 is just completely irrelevant if we want to know something about space-time and not just know that space-time is functional, because then we have to follow path 1 anyway and find out what this function is. And if you feel that way, I'll offer just a tiny element that may give you some reason to continue listening for another 40 minutes. And that is if it's true that space-time is topic neutral, we should not regard the realization of space-time in a quantum theory of gravity as too remarkable. So perhaps it is such that space-time occurs in more or less any theory of quantum gravity we could think of. So it's not, and this, I mean by here, it's that space-time is realized in a quantum theory of gravity should perhaps not be regarded as an indication that this theory has any truth to it. So this may be old news to anybody here, but at least the string theorists I used to work with in Copenhagen saw it as sort of they would pride themselves of the ability of string theory to give us general relativity and say, well, here we got good evidence why string theory is a contending theory of quantum gravity. If it's true that space-time is topic neutral because it's a function, then we should expect maybe that space-time is realized in almost any quantum theory of gravity, and therefore it's not anything that is very interesting or a very interesting theory or feature in a theory of quantum gravity, other than, of course, it has to realize space-time. Okay. So let me initially say a bit more about functionalism, both in the context of consciousness and space-time, sort of offer structure to an argument that indicates topic neutrality on the part of space-time. Then look at actual realizations of space-time in theories of quantum gravity and whether they could indicate multiple realizability, and then try to strengthen the case for multiple realizability by investigating a relationship between space-time and entanglement. Okay, so first we have this argument by Putnam that observes that many terrestrial creatures can feel pain. So if identity theory is true, then there must be some physical chemical kind that is common to this wide variety of creatures. Or, alternatively, pain is multiple realizable, so it can be realized by many distinct physical kinds. So this is the distinction between, again, identity theory and functionalism. Okay. So the idea would be to say multiple realizability indicates topic neutrality. And topic neutrality, again, implies functionalism, or at least it implies, or at least it refutes something like identity theory. And then the hope is that that sort of establishes functionalism by eliminating the option of identity theory. Okay, so the obvious question is, well, how do we establish multiple realizability, beginning in the case of mental states? Well, we could say if we observe that all humans could feel pain, we wouldn't be too surprised. Maybe even finding that all mammals could feel pain, we would still say, well, there could be some common physical chemical kind that we could identify pain with. But maybe if we found that an AI or silicon-based alien realized pain, then we would be more convinced that perhaps it is such that pain is multiple realizable, therefore topic neutral, and generalizing the argument that mental states are functional. Okay, so this would be the idea. Defend multiple realizability by shrinking the space of possible common physical chemical counts to something that's unacceptable. Obviously, I think identity theorists could always try to find something that all these creatures have in common. And then say that is what pain is. And I'm not sure we can give any good argument against that sort of view, but at least this is the general strategy, trying to eliminate the types of common physical chemical kinds that the identity theorists can point to. Okay. The problem is that this leads to immediate problems. Are we confident, we could ask, whether we can identify an alien's pain, whether we can whether we can know that an alien realizes pain? So perhaps we need to know what pain is in order to know whether alien realizes pain. So more generally, you have to know what pain is in order to know whether it's multiple realizable. And supposedly, if we know what pain is, then we know, for instance, whether it's functional or not. And then we don't have to go through all these iterations and arguments concerning topic neutrality. But I think the sort of solution you're often offered would be, well, if I stomp on your foot, then you know what pain is. You got some access to what pain is, and that should perhaps help you identifying even the aliens that realize pain. I'm not sure this is a very good solution, but it's good to be aware of this problem, because if we are to adopt this sort of methodology for space-time functionalism, then we have exactly the same problems. So we could argue in favor of space-time functionalism by eliminating the possibility that there is a common shared physical kind with which we can identify space-time. And the obvious questions are, of course, how we identify space-time, and whether we have a conception of space-time that is neutral between this space-time functionalism and this space-time identity theory. And I'm not sure I have a very good answer to this. In this sense, this is very programmatic. But perhaps we could say, regardless of what space-time is, it's the sort of thing that is realized by general relativity. This is very conjectural. So we could maybe say, and that's what I will do here, if a theory reproduces, and notice this parenthesis, enough of GR, then the theory realizes space-time. So it's sort of, we are helping ourselves to a notion of space-time that doesn't involve actually identifying what space-time is. We just say GR realizes space-time, so if we find theories that reproduce enough of GR, then we're satisfied that the theory realizes space-time. Okay, so let's look at realizations of space-time in quantum gravity. So Chris and Nick has this useful taxonomy of different theories of quantum gravity. So we can have these non-metrical lattice theories. Among them, we include causal set theory. So this is a type of theory of quantum gravity. We can have spin network theories that also feature some sort of discrete, and we could regard it as a lattice model as well, but it does not have a notion of locality. So spin networks are arguably distinct from these non-metrical lattice theories. And among the spin network theories, we count loop quantum gravity. And then finally, we got variants of quantum field theories that try to incorporate gravity, and among them, we have string theory. So we can say these are different ways to solve this issue of quantum gravity or incorporate quantum mechanics and general relativity. Okay. So now let's make the observation that we find, and this is where it gets very conjectural, I'm sorry, but we find indications that in all of these theories of quantum gravity, we find something that could, in the end, be GR. So in causal set theory, we conjecture that some sort of Lorentzian spacetime could obtain as an approximation from these discrete causal sets. I'm no expert on causal set theory, so I can just quote whatever it says in the Stelker paper. Similarly, in loop quantum gravity, we have these various attempts. Chris has recently surveyed them to obtain GR from some semi-classical approximation, and then we take a classical limit of these spin networks, and then supposedly we get something that looks like GR. And then finally we have string theory, where we get at least the Einstein equations as equations of motion to first order and perturbation theory in the string length and the string coupling for the closed string. So bear with me here and just pretend that we got convincing reasons that space-time is realized in all of these theories. And obviously this is very contestable, but it's sort of to show how this argument will go. Okay. So the argument for multiple realizability could now say, well, according to the taxonomy, string theory, loop quantum gravity, and causal set theory are very different theories. Or at least they are examples of types of different approaches to quantum gravity. Yet, we could say all of them realizes GR. And since we just assume that GR realizes space-time, then we say based on that space-time is realized in these theories. So we could say, oh, maybe this is the space-time equivalent of finding three creatures. A carbon-based, a silicon-based, and maybe a boron-based creature that all realize pain. And this, supposedly, would be good evidence that pain is multiple realizable. And similarly, we could say this is good evidence, perhaps, that space-time is multiple realizable. Okay. However, there is an, I think, obvious objection to this argument. Suppose we are at the intergalactic gathering of conscious beings, so we got representatives of all the conscious beings that live in the entire universe. And we go around there and we try to find pain-realizing creatures. There are hundreds, maybe thousands of creatures, and we happen to find three pain-realizing creatures. Whereas this sounds like an argument in favor of, I can use the pointer, wait. This sounds like an argument in favor of multiple realizability. This story sounds like we just happen to find three creatures that realized pain among a lot of creatures that didn't realize pain. So it seems probable in this second case that there could be some common physical kind that we could identify pain with, and therefore avoid having to adopt multiple realizability and the conception of pain as functional. Okay, so we could ask the same. Is the realization or the conjectured realization of space-time in these three theories just an artifact of the kind of theories we might find interesting to pursue? So obviously we are interested in theories of quantum gravity that somehow realizes space-time. If we find a theory and we think it has there's no way for this theory to realize space-time or for GR to obtain some approximation of this theory, then we wouldn't even find it interesting to look further into. And in this way, we could say having three theories that are conjectured to realize GR and therefore space-time is similar to finding three pain-realizing creatures at the intergalactic gathering of conscious beings. So we need something else, or at least it would be nice having a further argument in favor of multiple realizability, the multiple realizability of space-time in quantum gravity. Okay. And furthermore, there is another problem that's just only based on a very recent conjecture. So we could say, well, maybe this at least does render it implausible that there is a common kind that can be identified as space-time between these theories. But Verlinde has recently proposed that there may be a deep relationship between string theory and loop quantum gravity. So that could exactly indicate the sort of shared physical kind that we could identify space-time with, rather than having this being indicative of multiple realizability. And perhaps we could think that the same goes for causal set theory, that it could be integrated in this picture proposed by Verlinde as well. So what I will do is offer a further argument that space-time should be regarded as multiple realizable. And this relies on a relationship between space-time and entanglement. Okay, so I won't go into the details of entanglement, you know what that is. But what is interesting about entanglement is that it's really low maintenance, in the sense that all we need for entanglement to obtain in the system is that we got quantum degrees of freedom. We got 2 or more quantum degrees of freedom in the system, then we can have entanglement. But, and this will be a claim, and I think I would be happy to argue further for it, that just being a quantum degree of freedom does not qualify as a common physical kind. So we can say many types of systems have quantum degrees of freedom, which I take to indicate that entanglement, at least, is multiple realizable. We can discuss this further, I would be happy to. But take it as a conjecture so far. Entanglement is multiple realizable. Okay. So maybe we could construct an argument to the effect that space-time is multiple realizable based on a relationship between space-time and entanglement. So I propose this. If we say all theories that feature entanglement, what we call entanglement theories, realize space-time. So then we say entanglement is multiple realizable, from which it follows that space-time is multiple realizable. So that would be the idea of an argument. If entanglement is multiple realizable and there is no common kind shared between all entanglement theories, that would be what would be entailed by this claim that entanglement is multiple realizable. Then if all theories that feature entanglement are space-time theories, then this must still hold that there's no common kind shared between all these theories, and therefore space-time as well is multiple realizable. Now, obviously, the premise one here is very problematic and highly speculative. I think some would defend it. I may defend it sometimes, but we can think of a less contentious argument that unfortunately is less strong as well. So suppose that in loop quantum gravity, causal set theory, and string theory, we find that space-time can be encoded as entanglement. And as we claimed, entanglement is multiple realizable. Then either space-time is also multiple realizable, or we found 3 entanglement theories that nevertheless happened to share a common physical kind. But no, if one is independent from the fact that these 3 theories, causal set theory, loop quantum gravity, and string theory, realizes space-time, then B is an additional assumption that the space-time identity theories has to adopt. So this is sort of building additional evidence in favor of multiple realizability, obviously on the condition that we can show something like 1. And I think we got good indications that it is the case that in these theories, loop quantum gravity, causal set theory, and in string theory, that space-time can be encoded as entanglement. Okay. So some of you may be familiar with the ADS-CFT correspondence. So this is a string duality. It's a duality between 2 different string theories, but most often expressed as a duality between a 4-dimensional n equals 4 super Yang-Mills theory, and then a type 2b string theory in 10 dimensions on ADS5 cross S5. So the idea is something like this. We have a quantum state in the super Yang-Mills theory, and it's dual to some space-time. And this quantum state is often said to live on the boundary. So it lives on the asymptotic boundary of the ADS spacetime. There are some subtleties here. The interesting thing is that we got this duality, or at least we have this duality is conjectured to hold, and it suggests that there is a relationship between gravity theories, these type 2B string theories, and then super Yang-Mills theories in 4 dimensions that are conformal field theories. And furthermore, it's found by Ryu-Takayanagi that there is a specific relationship between the entanglement entropy of a region in the CFT and then a particular area in the ADS. So it goes something like this. Consider we have a Cauchy surface in our CFT. Now we subdivide it into 2 different regions. We call them B and B bar. So now we subdivide this Cauchy surface into 2 different regions. Now we can associate an entanglement entropy to the region B by looking at the reduced density matrix of this region. So by this we can define an entanglement entropy of the field theory that lives on this region B. Okay, and now Ryu-Takayanagi finds that this entanglement entropy is equal to the area of a surface in the ADS spacetime that divides the boundary into these 2 regions, B and B bar. So this is the B tilde on the figure. It's this line, if we can say so. So it's a surface in the bulk. And we see this is very similar to the Bekenstein-Hawking formula. There's no coincidence, because we can show that it applies in the particular case where we got a black hole in the ADS spacetime, and it's nicely reproduces the result of the Bekenstein-Hawking formula. But we won't go into this in this case. All I'm saying is there is a relation here between 2 empirically equivalent theories. So we got the CFT, and we got the ADS. And the information that has to do with the connectivity, we can say, between these 2 regions, or the surface separating this region from this region in the ADS spacetime, is related to the entanglement entropy between this region on the CFT and this region on the CFT. So something happened now. Oh no. I mean,
access to the computer.
French.
Let's try again. Doesn't do anything?
No, doesn't matter. You use the computer.
No. Yes.
Okay. So yes, just take that one. So one way to get an intuition how this relates entanglement in spacetime, we can consider what happens when we remove entanglement between these 2 regions. So this, now we're looking at the cylinder from the top. So we still got the CFT here on the boundary, if we can say so, then the ADS spacetime in the bulk. And when we reduce the entanglement entropy between these 2, the quantum states in the CFT, what happens, according to the Ryu-Takayanagi formula, is that the area of this surface shrinks. And in principle, if we remove all entanglement between the quantum systems living on B and B bar, these 2 regions of spacetime, bounded by B and B bar, will pinch and pull apart. So somehow the entanglement in the CFT encodes the information about spacetime on the ADS side. So yeah, that's the basic idea. There's a relationship between spacetime and entanglement. And Going to the other theories we consider, so this was in string theory. What's interesting is that recently there's indications that both in causal set theory and in loop quantum gravity, this Ryu-Takayanagi formula holds as well. So also in causal set theory, well, the results in causal set theory are, again, very conjectural. So they did simulations and found agreement with this formula under making a generalized definition of entanglement entropy, and then looking at nodes in the causal set. But nevertheless, they found agreement with the Ryu-Takayanagi formula. And similarly, in loop quantum gravity, Smolin has argued that we should find something like the Ryu-Takayanagi formula in loop quantum gravity as well. And this result has been generalized to generic group field theory approaches by Chirko, Oriti, and one more, just very recently. So the conjecture, or what is indicated by this, is that it is actually the case that in causal set theory, string theory, and loop quantum gravity, space-time can be encoded as entanglement structure. Okay, so that was the ingredient we lacked in our argument. So if it's such that space-time can be encoded as entanglement structure in these theories, and it is such that entanglement is multiple realizable, then string theory must be, then space-time must be multiple realizable in these theories, or we have this option B that there is some shared physical kind that we can identify, even though or as I said, causal set theory, loop quantum gravity, and string theory share common physical kind, which is then supposed to be space-time, despite being rather different types of theories, and that space-time in these theories are related to the topic neutral entanglement. Okay, so the idea would be from A, it follows that space-time is topic neutral, at least multiple realizable, from which it follows that it's topic neutral. And that would refute space-time identity theory. So what I propose to have shown here is a route one could take to defend space-time functionalism that does not involve exploring the functional role of space-time. We can just, hopefully, explore whether space-time is realized in these various theories and then eliminate the possible shared physical kinds that identity theories can point to as what they identify with space-time. The upshot of this is precisely the versatility of space-time. So the fact that space-time is a rather versatile thing that we expect to be realized in a lot of different theories. So just because a theory realizes space-time is not evidence that this theory must have some truth to it. Perhaps a message that goes specifically to the string community. Okay. So this is more like a little extra thing. So maybe if it's such that there's a general relation between space-time entanglement, then as Chirko et al. proposes here, the RT formula strongly supports a general relation between entanglement and geometry, in turn leading to the suggestion that the whole of space-time geometry can be understood as emergent from properties of non-spatio-temporal quantum building blocks. So what I take this to suggest is that perhaps if there is a generic relationship between space-time and entanglement, we should actually expect that any quantum theory of gravity realizes space-time, because any quantum theory of gravity must realize entanglement. Obviously, this relies a lot on whether it's true that we can generalize this relationship between space-time and entanglement, but at least I think it's an interesting idea that any quantum theory, basically, realizes space-time in some sense. Okay. Now, this leads us to a final puzzle, I think, or final sort of thought experiment we can carry out when it comes to space-time functionalism. So part of this relationship between space-time and entanglement that we may or may not buy into is the general framework of the gauge-gravity duality. And the gauge-gravity duality implies, among other things, that there is a duality between fluids and gravity theories. So gauge theories can be approximated by classical fluid dynamics. So, and especially the dual spacetime then proves to be a class of certain black hole spacetimes. Okay. So this is interesting. There's a relationship between classical fluid dynamics and certain black hole spacetimes. So this could be very interesting. Perhaps we can use our understanding of black holes to explore the Navier-Stokes equations. Or perhaps we could simulate a black hole on a hydrodynamic system and learn about mass and rotation laws. This has exactly been done by Weinfurter and others, I think, primarily based on research on the University of Nottingham. Okay, so this leads me to the final slide, namely a Chinese room of space-time. So there's a lot of supposes here, but maybe you see where this is going. So suppose we have a hydrodynamic system that simulates a black hole, like they did in this experiment conducted at the University of Nottingham. So if it is such that space-time is what space-time does, and the fluid gravity correspondence actually obtains, then in some sense this fluid dynamical system or hydrodynamic system that simulates space-time, or simulates a black hole, is really a black hole. Space-time is what space-time does. And obviously the space-time identity theorist echoing Searle will say, obviously, this fluid is not a black hole. It's perhaps simulating a black hole, it's doing something black hole-ish, but there's more to being a black hole space-time than just realizing the space-time function. So this is perhaps not an argument against space-time functionalism. So that was all the various thoughts I have to share with you. Thank you.
Okay, Chris.
Thank you. So I have various points, I think, where I disagree with you.
Yeah.
Not sure where to start. Here's one. I'm a little bit puzzled by the claim that because in all or some different approaches to quantum gravity, there has to be, or there does in some sense, speculatively, sort of emerge a formula that the Ryu-Takayanagi formula. Therefore, we have entanglement because in the original case, this comes from an entanglement entropy. Therefore, it's multiply realizable, and so on and so forth. Because causal set theory is a classical theory. And I don't know the particular paper you cite by Sorkin and Diasti, but it's presumably not a quantum version of causal set theory that they look at, but a classical theory. So I don't see how this is an entanglement entropy. Presumably it comes from some other statistical background entropy, some sort of counting argument or something.
It does.
And then it seems like that would certainly not be an example of entanglement being realized.
You're right. It's based on a counting argument. So the supposition in the paper is to say, well, we in the classical context we got indications that indicate that some relation as proposed by the Ryu-Takayanagi formula holds between this entropy and then areas as defined by collections of nodes. And then there are really, it's really a stretch to then suppose that this reproduces, as they claim, the Ryu-Takayanagi formula. So I completely agree with you. That paper is very contentious. So I'm just offering you what the recent literature claims. So I would certainly agree with you. It's not. There's no evidence yet that causal set theory gets reproduced in Ryu-Takayanagi format.
A second question is sort of concerning the bigger argumentative for dialectical situation here. Why should you have the slide back up at some point where you said that entanglement is multiply realized, entanglement theories or theories with entanglement or so rely on a space-time background or have a space-time background, therefore space-time is multiply realized, or maybe I'm not completely correctly reproducing it, but it's something like that. And I think that does not seem to follow at all. Something else is needed, because it could be that all these different theories which multiply in different ways realize entanglement may nevertheless have the same old plain vanilla space-time as a background, and it would not follow that the space-time that they use is multiply realized.
Yeah, so the argument is not based on this entanglement being realized in space-time. It's really based on the conjecture that entanglement can encode space-time. So in the ADS-CFT correspondence, we find that we can encode some of them. Yeah, so that was what I was trying to get at. So it's really important that this is encoding space-time and not just being in a space-time background, because then you're perfectly right. It's not showing anything.
I think I was a little bit confused because I think that was only coming at the next slide.
Oh yeah, okay, yeah. So good. Thank you.
Did you still have a question, Walter?
Thank you for the talk. I have also some comments, but maybe just quick one about this slide.
Yep.
I think here it's the point is that with respect to the Chinese room analogy, is that here you have these fluid-based models reproduce certain features of possibilities, but certainly not plays a functional role of the black hole as encoded in GR. So in this sense, it's clear that there is a disanalogy.
Depending on your view on this correspondence. So if the correspondence actually obtains.
No, take a black hole in GR, and all the ambiguities, the global features, the purely geometrical aspects of the black hole, they are not going to be reproduced by definition in these fluid-based models. Which doesn't mean that these models are not distinct. They capture a lot of things, a lot of physics, probably. But if you look at the functional role in some sense, that clearly you have this analogy there.
But so what would you say in the case of general ADS-CFT correspondence, where we, for some reason, can have a gravity theory and then a conformal field theory that nevertheless are empirically equivalent? So my intuition would be all the degrees of freedom on both sides must be the same somehow, even though they appear to be very, very different. If this fluid gravity correspondence is the same, then even though the degrees of freedom look incredibly different, then nevertheless they must realize the same function.
The example you give about duality, this is much more speculative, and if you have a mathematical duality, then this is something else. But here you won't have such correspondence, by definition.
True.
There are going to be global aspects, global features of the black hole which are not going to be encoded in this fluid case.
Yes, I agree.
This is not, at best, going to be a subset of the types of black holes you can model. Or something like that.
It's only certain kind of rotating black holes you can model in this way, as far as I know.
Thank you.
So I think we had Eleanor, Niels, Tushar. Did you still have a question?
Yes. So it was. Sorry, I got massively distracted by the disaster at home. So no one just asked about the Chinese room, right? This doesn't. I mean, the Chinese room of space-time doesn't seem like the right kind of thing at all. I mean, a dumb hole in fluids is playing a functional role with respect to a completely. Nobody thinks the Chinese room would work if you had something that roughly instantiated the functional role, but the inputs and outputs were nothing to do with people, or they were like tables and chairs. Like, And I mean, this is just a completely different scenario. I think this is completely disanalogous. I mean, it might well be that if you have something like a black hole, what goes on inside black hole isn't the point, and if you had something that behaved exactly like a black hole,
Yeah.
with respect to all of ordinary dynamical systems, that would be an analog of the Chinese rim, and a functionalist perhaps should bite the bullet.
Yeah.
But, although, I mean, it's not clear that functionalist is, I mean, the definition of black hole is different from the definition of a space.
Yeah, surely.
But you create I mean, the whole point is there's meant to be an analogy between fluid inputs and
Yeah, so at least as the correspondence is formulated, what do you say? The solutions, the GR solutions can be mapped into these hydrodynamic systems, and then somehow we can. They do this. They try to learn about the Navier-Stokes equation by reformulating these fluid dynamical problems into problems about black holes. And then they explore these black hole solutions, and then they try to translate back and learn about the Navier-Stokes equation. So this work is done.
Yeah, so of course, there's questions about confirmation by simulation, but nobody thinks that a fluid is a black hole, and nor should the space-time functionalist. That's just
Okay.
If you verify, I mean, the whole network of theoretical relations,
Yeah.
then that's, I think, the idea.
Yeah, sure, but I mean, I don't have to ramify what a fluid is. I know what a fluid is when it's at home, but
But then what about the ADS CFT correspondence? So you say the same, that the ADS spacetime is not the CFT spacetime. They may be empirically equivalent, but this one is a gravity theory and the other is just some conformal theory, regardless of what the evaluation of propagators then tell us. Does it make sense?
I think the situation in ADS CFT is extremely different because you're dealing with something that's highly theoretical you don't have independent access to. I mean, getting a corkscrew is a functional concept.
Yeah.
But I don't think if you develop something that functioned a bit like a corkscrew for something that had nothing to do with corks, you'd have made a corkscrew.
So you think if we had actually lived in a ADS5 cross S5 type 2B string theory world, we could actually assess that it was such a world and not a n equals 4 super Yang-Mills theory world.
I don't know the answer to that question.
Me neither. I hope.
I don't think this is analogous.
Okay, great.
It's just very specific. Like we're talking about, a situation where we have access to kinds of physical systems that are affected by black holes, and then we, in theory, have an analogy between the relation of some piece of fluid dynamics to a whole different set of systems. There should be no part of functionalism that when one has completely independent reason to believe that, a spaghettified person falling into a black hole is a different system from a bit of water in my bathtub.
I agree. It sounds very, very reasonable. We can discuss this further. I think it's not as disanalogous as you think, but it will take us too long.
I think the reason that I think it's disanalogous and that there's a case in something like string theory is this question of how the different parts of the theory are sort of coming by their reference and their. It's different. You're a long way from empirical stuff. The question of whether two things represent the same physical thing is a really, really tough question. When I'm looking in my bathtub and asking, when I'm looking out in space, and I go into this Milky Way and wash my bathtub and said the same thing, I don't have the same.
Which is which? Oh, I see where you're going. Okay, great, thank you.
So just this main question of the setting. So you basically say that space-time in different approaches to the gravity is somehow encoded as some kind of entanglement structure, right? So which level is this entanglement structure? It's a fundamental level in these approaches?
Yes.
Okay, so
in this, I know literally nothing about the causal set theory or the loop quantum gravity context. I know a lot about the string theory context, so I can tell you more about how it works there. If you
more a claim about universality or something like this, that all these structures from these, or not all these certain structures from certain approaches share a common feature, namely that they encode what is like space-time, or what is still like space-time, some form of entanglement. But why is this a statement about multiple realizability?
So the statement about multiple realizability relies on our supposition that these theories are different enough so that they don't share something that we can point to and say this is what space-time is, and so we say this is the element present both in string theory, causal set theory, and loop quantum gravity that we then identify as as space-time.
Yeah, but it's not really like in many other cases of multi-realizability, you have some kind of underlying structure which leads to the same outcome, but rather than always fundamental structure, all these structures share the same feature, right?
Yeah, okay, so then I misunderstood. So the multiple realizability claim is exactly that there's no such shared feature. That the fact that these different theories realize space-time is not a consequence of there being a shared physical kind in all of these theories. They have very different degrees of freedom, and somehow all these different theories can nevertheless realize space-time. And that's why we could think that space-time is multiple realizable.
But which space then?
So
Entanglement structure?
Conjecturally GR or parts of GR.
But then you could just say that for any kind of approach which in the limit gives GR, that basically, I mean, what's so special in what's entanglement? I mean,
the entanglement part is just further corroborating this view. If you say maybe there is a shared physical kind between these different approaches to quantum gravity, then the entanglement argument offers you additional, perhaps it offers you additional reasons to believe that there's multiple realizability in this case.
but why not just generalize the whole thing and say, rather than just looking at entanglement, whenever I have some kind of limit leading to GR, this shows them, we think there can also be other limits leading to GR. So whenever I have the sequence xn leading to x as a limit, I will also find another sequence yn which also leads to x. So I can claim that x is multiply realizable, why just limit as arguments into.
Because the entanglement bit is very, very hypothetical and relies a lot on ADS-CFT correspondence, which remains a conjecture. And in the context of loop quantum gravity and causal set theory, this is, as Chris pointed out, in causal set theory, it's very, very early work on this, on whether this is actually realized. This relationship between space-time entanglement is realized in causal set theory. And even though the Smolin, the loop quantum gravity paper, tries to make it sound as though we got more or less the Ryu-Takayanagi formula, there's still a long way to go before they have anything resembling this holographic relationship that we have in string theory. That is realized as well in loop quantum gravity. So that's why I'm reluctant to let this rely on the entanglement argument alone, because it's wildly speculative.
Okay, really just like this.
Yeah.
So yeah, thanks for the talk. In a sense, is it just a clarification on some of the kinds of things that both Chris and Niels were talking about? But just sort of, I'm not quite able to track the entanglement space-time like on sort of pretty basic formal grounds, which is that when you talk about entanglement in a quantum system, that's a claim about how a Hilbert space for a system decomposes into tensor products of smaller Hilbert spaces, right? And so correct me if I'm wrong, I wrote topic neutrality next to my question, and I can't remember exactly when you related this to the entanglement, but it seems like the idea that entanglement is a sort of universal feature of quantum systems is a claim about whatever Hilbert space we have, entanglement will give us information about how it decomposes into smaller Hilbert spaces.
Yes.
It seems like a completely different kind of universality that's at play when you talk about space-time, right? So depending on sort of how you want to think about the ontology of quantum mechanics, you might think of sort of density operators associated with regions of space-time. Obviously I'd say that, but sort of whatever else your story about sort of the relationship between space-time and sort of it's sort of the relationship between space-time and Hilbert space. How do you get from one to the other?
So the conjecture by Mark van Ramstung and a lot of collaborators is that in principle this is a heavily overdetermined problem. So we can decompose our CFT into a lot of different Cauchy surfaces. We can make a lot of different decompositions of this Cauchy surface into various regions, which gives us a lot of entanglement entropies. And then we can look at the corresponding surfaces in space-time, and then so all these entanglement entropies should significantly overdetermine the space-time corresponding to it. So we, in that sense, all the entanglement information about the entanglement entropy, which must be somehow encoded in the entanglement, is enough to get us the space-time. Now this is formally it's a very difficult problem to solve. I know of no examples where someone actually did it, but in principle it's highly overdetermined. So I think, at least if we buy into the ADS-CFT correspondence and the Ryu-Takayanagi formula, it's certainly the case that the entanglement on the CFT side encodes all the information about the space-time on the ADS side.
Just a quick follow-up. No, I don't mind. Yeah.
Carlos?
A couple of, from the one side, there is this. I see that there is a qualitative measure in what you compare this identity, because for sure there's going to be a lot of theories that do not encode space-times, single space-times as we know it. And from the other side, there are many theories that they could lead to something like space-time.
Yeah.
So I think that once you have in a complete set of theories, you have some subgroup that they really lead to something, then you can almost for sure you will see something within this group that is shared by all of them.
That
you know, maybe what you find is not. So at the end of the day, whether calling this identity or not is some sort of qualitative statement.
Yeah, okay, so you say, well, regardless of how different they are, we should find something that they share in common, and then we would say, then that is what space-time is.
I mean, I can construct, for sure, you can construct theories much complicated than that, than those, in which there is no any sort of, for example, if you go to these Pinzler geometries, I can build theories based in Pinzlerian structures, and then in these structures you will not get anything related to general relativity in general. And then you can have many of those. So at the end is that I think that in theories that are able to get something similar to GR, almost for sure they will share something. I don't know exactly which is the thing that they will share.
But is that which is share is space-time?
Yeah.
Okay.
No, well, is this? I mean, they share something that maybe should be rephrased in a different way, not only because they have this space-time, but they will have, in terms of complementary systems. What happens is that they have symmetries. You have systems that are very different, but at the end they have at macroscopic level they have the same sort of symmetries. And then you say, well, these two things are part of the same universality class, even though the system itself, if you look at them microscopically, are very, very different. So I think that both, I would buy both things. I think that if the take into the identity theory is not too extreme, that meaning that because you share something, you are equal. I don't think that because you share something, you are equal. You can be very different, but still share something. It's the same idea that I have with the languages. I mean, if you analyze all the languages in the earth, you will say, well, they don't have anything to do with each other. But then when you analyze other issues, you see that they are similar because all of them are coming from our brain structures.
So that sounds almost like an argument against space-time functionalism.
No, not at all. In fact, I would. I would not think that this is.
So it's functionalism without topic neutrality.
Yeah, but the thing is that, as I said, it's a kind of intermediate stage.
Okay.
That's what I was saying. That I think I'm very into this multiple realizability. But this doesn't mean that you have to. That multiple realizability means that any theory is going to lead to the same.
No, I agree. That is based on this very wild speculation that the relationship between entanglement and space-time just generalizes to everything. Because then if there's a general relationship between, so if it is such that all entanglement theories are space-time theories and vice versa, then obviously any quantum theory of gravity will have space-time in it. But whether this is what that would even mean, and what these space-times would be, or whether they would be anything like the sort of thing we would want to call space-time. This is the physicist speaking, and I'm not sure whether it's very precise use of language to say that we have an indication of a general relationship between space-time and entanglement. At least space-time means something very different in this case.
We should probably stop soon. There's 3 more. Maybe the 3 of you that still want to ask questions can do it after the session. So that's, thank you, Rasmus.
Is one of you going to say something about tenet?
Yeah, there's dinner at 7 o'clock. Perhaps we pick it up, perhaps we can meet 10 to 7 in front of this building, facing the street.
Do we? Does everybody understand the rules of reimbursement and what they can get?
Speakers get the meal paid, crew members. No other way around, no crew members and non-speakers don't get any kind of question.